Good evening, Dr. Bhardwaj. Is, can you?
Yeah, hi.
Hi.
Hi, good evening. I think I can, I'll also join from my, am I visible
Yes,
now?
yes,
Yeah,
yes.
yeah. So I'll be giving more of a, not a presentation-based lecture, but more of a written notes kind of lecture. Well, mixed bag.
Written notes is
So,
good. Written notes is,
yeah,
I
it's
like it
slower.
better.
Yeah, I think it's also easier to understand because otherwise it's very easy for me to go super fast.
Yeah. Somehow it is also more interactive. I mean, if you do
Yeah,
slides,
that's what I thought as well.
so I'll let you take control whenever you are ready because we are already
Sure.
on.
Yeah. I just need to somehow figure out how do I share my screen on.
So
How,
you on the bottom you see a up arrow. There is
yeah,
a,
yeah. So,
if you click that, then you can see a list of content. So on the left hand side you can share your full screen, but you can select the window on the right hand side. So if you look at
oh
the
yeah,
window,
yeah.
so you can
So
choose to share
let's
whatever you
see.
want. Yeah.
I hope you
Yeah.
can see my screen.
Yes, we can see some white. I mean, it's a slide, I think.
Yeah, it's a
Yes.
slide. So
Hmm.
I'll be writing on some of these
Okay.
slides.
Okay.
So,
Okay. Sure.
yeah, because bunch of stuff is also kind of nice interactive anyway. So
Okay.
yeah.
Okay. You can start whenever you are.
Uh, yeah, I hope everyone else can hear me well as well. Um, just a, brief kind of uh, overview about this particular work that I'm going to be talking about. And I'm not sure how many of you are actually familiar with the idea of um, what knapsack sets are. If you have had some background in discrete optimization, you might be well aware of those. However, we're not going to be talking about just the general sort of linear knapsacks. We'll talk about something very interesting here, which is sub-modular knapsacks. And this is a joint work with Alper Atamturk at Berkeley. Um, and before further ado, let me just start. Knapsacks are, why are they interesting? Just start. What some modular knapsacks are, sort of applications of studying these sets. So I'll just draw the motivation starting out, and we'll carry on with that example as we go along. Please stop me at any point you feel that you're not understanding something, or if you know, it's very easy for me to assume that you already know something. So if something is not clear, please feel free to stop me. Um, so let's see. Um, so as I said, never mind. Um, so as I said, so the motivation of that I want to introduce um, this topic with is specifically the application of network design with uncertain capacities, right? So if you guys are not aware of what a network design problem is, a network design problem essentially entails that given a set of nodes and set of arcs that connect those nodes, um, how do we optimally, and that cost, you could have any objective function that either provides a proxy for your cost, or you can have kind of explicit cost measure that minimizes that cost to send some flow from your source set to your sink set, right? So these are some candidate nodes that you have available and some of the arcs, that connect them. So our goal primarily is to figure out which nodes and which arcs should we choose So essentially designing the topology of this network such that we are able to send some flow from the source set to the sink set. And this is a very well-known hard problem. It generalizes the Steiner tree problem. It's an NP-hard problem, which is to say that the solution times specifically do not, they grow exponentially with respect to the size of the problem or the data of the problem, right? So now different parameters of a network design problem could be the fixed costs of setting up these arcs and these nodes. So think, for example, you know, that if you were setting up a water network, or if you were setting up um, a gas pipeline network or an electricity network, or just not, if not anything else, just an information transmission network. So everything comes with a fixed cost. You might have variable costs of sending a unit flow on these arcs specifically, but the specific parameter that we'll be focusing on is the capacities of these edges or arcs, right? Um, so we're not concerned about the fixed costs and the variable costs. Let's say, that we don't have any variable costs. So the primary thing that I'm going to be concerned with today
So
is going to be the capacity.
one of the participants has raised hands. Do you
Yeah.
want me to do
Yeah,
you
yeah, sure.
so
Yeah.
Mr. Dibyendu Bhattacharya, you can ask question. You can unmute and ask question if you want. Do you want to ask question?
Actually, sorry, sir. When joining, it was by default. That hand was
Oh,
placed,
that's
sir.
okay.
You click it
It
again and it
happens.
will go down.
Okay, thank you, sir. Sorry,
Okay,
sorry, sir.
okay, okay.
Sure. No worries. So as I said, let's focus on these capacities, right? So how would you generally formulate this problem if you had the task of formulating this problem where to figure out some, so your decision variables essentially become which nodes or to pick while designing this network, and the the most natural constraint that you can come up with is that you want to somehow pick a topology of the network such that on that network, if I partition the nodes, so consider this partition of nodes, right? So all the nodes here and all the nodes here. So with respect to this partition, all the edges that are going from, let's call this partition source set, let's call this partition the sink set, all the arcs that are going from source to sink must have enough capacity such that they can support the flow that I'm trying to send across, right? It's almost like, yeah, if you want to send a flow through a pipe, and if a pipe does not have cross section enough to support the flow, how will you ever, send the flow through it? So that's a very natural constraint that you can think of. However, what if these capacities on these arcs were actually not deterministic anymore? They were stochastic or they were probabilistic. They were coming from some uncertainty set, right? So this constraint that defines a deterministic feasible set no longer defines a deterministic feasible set, right? Because now your constraint is going to be um, summation over all the edges in this ST curve, some psi, and if these psi's, that is the capacities on these edges, are not deterministic, then this set in general does not define a deterministic set, right? So how do we even optimize over it? That's a fair argument. So that is what we are trying to, that's what we are going to see. I mean, in the cases, so specifically, so this project specifically started as a DoD fellowship project, and primarily with respect to information transfer. So let's say you're trying to send a piece of information from a particular node to another particular node, and the bandwidths of some communication channels need not have they need not be deterministic, right? They can keep changing over time. So in the case when the network traffic is super high, how do you ensure that you're able to send that flow, because that operation is super critical. So when the cost is super high of failure, how do you ensure that with respect to changing bandwidths of these arcs that are carrying the flow, that these this ensuring that the flow kind of goes from source to sink, um, sort of um, so that particular thing is ensured, right? So that's the primary motivation. Now, at least with this at the outset, is this outline clear to everyone? I hope that is clear. So if there are any questions, feel free to ask, because we'll build on this outline and we'll see how submodel knapsacks can help us. So if not, then let's move forward, right? Now, as I said, that we had constraints of these form, as I said. So we were specifically dealing with in the previous slide constraints, a summation over some indices and some parametric ease and some set. And so if you have a linear probabilistic constraint, since it does not define a deterministic feasible set, it's actually fair to ask that instead of asking this, or instead of constraining via this constraint, it's actually better to say that the probability, or ensuring some service level on the satisfiability of this constraint, right? So saying that the probability that this constraint is satisfied is greater than or equal to some service level that or some value that I make sure satisfies me, right? So for epsilon between 0 and 0.5, if I say that the probability that this constraint is satisfied is greater than or equal to 1 minus epsilon, and if indeed your parameters are distributed normally, then this constraint, um, this particular constraint, has an exact deterministic representation, which is as shown here, right? Where omega is just your CDF inverse with respect to epsilon. It's not too hard to see. So if so maybe think of this as an exercise where you try to, if you know the CDF and the PDF of a Gaussian distribution, then you can clearly sort of build this relationship that why this probabilistic constraint um, can be replaced by this exact conic quadratic constraint, or we also call them second order cone constraints. So this is essentially where u is the nominal value of psi, so the first and the second moments specifically. So this is u transpose x minus, or in this case, plus CDF inverse epsilon square root of x transpose sigma x, which is where sigma is your variance covariance matrix. And right, so the second order cone constraint um, is what you have in terms of exact representation. Um, Now, what is interesting is that here, even though we, assumed that psi is distributed normally, right? And it turns out that even if that is not the case, so even if you don't have any information about psi, so it's quite possible that your psi you empirically know only through the first couple of moments. Only through your So most often when you have data, um, and you know that it's coming through empirically, I mean, all you know is not the underlying distribution, but the first and second moment of the data. You can compute further moments, but let's say that these uncertain parameters are only known through the first couple of moments. Um, then in that case, you do not have an exact conic quadratic constraint, but a sufficient conic quadratic constraint. So you have inner approximation of these sets. So um, even in that case, we have a similar looking set where omega is, I mean, omega in first case where size were, distributed. Um, Normally, your omega was negative CDF inverse with respect to epsilon. And now it's a different scaling parameter. So when you know psi through only first couple of moments, your omega is defined as this new scalar parameter. But it turns out that this constraint here provides an inner approximation of this constraint. So any solution you get here is guaranteed to satisfy that probabilistic constraint, right? Um, Furthermore, if your psi is symmetric with support this, then even in that case, the same conic quadratic constraint is sufficient for this particular probabilistic constraint. Now that's all good, right? So we know that. I mean, here also with a different scaling parameter. Now that's all good, but how do you ensure, or where do submodular knapsacks kind of come into picture? So let's formulate our problem first. So our problem was, I want to send a flow from the source to sink, making sure that even with the uncertain bandwidths or capacities on the arcs, I'm able to transfer that or send that flow from the source to sink with some service level, right? So this is the robust formulation now. So you're minimizing some cost, um, subject to all such probabilistic constraints that we had. Um, so, right, so if you write this for me, so probability that summation over all cut sets, so these E will be in some cut set, and you'll write this for all possible cut sets, right? CS. Now, and we just learned that we can write these probabilistic constraint as something like this. Um, so that's taken care of. So we see how we can formulate this problem of minimizing a robust fixed cost network flow problem in this case of uncertain capacities, right? So that's something which is hopefully clear to everyone. The problem, if you can see, is that we're saying that we have to write this constraint for all the cuts possible. And if you have been following closely, then if I want to partition the nodes in a source set and a sink set, then how many possible total cuts would I have in someone? It's an interesting icebreaker, I hope. um, so can someone tell me what is the total number of cuts in a network if I want to partition the total nodes? Let's say we have total n nodes, and I want to partition the graph in two partitions, a source set and a sink set. Then how many such cuts can I have, or how many such partitions we can have? And it's just a simple combinatorial argument, simple counting argument. Um, so anyone? It's essentially going to be 2 to the power n minus 1. You can check that. Um, you know, so the cardinality of this set is 2 to the n minus 1, where n is the number of nodes you have. So clearly, if you were to add all these constraints, the problem is going to explode fairly quickly, right? So while our deterministic version of the problem was already NP hard, now I'm also dealing with exponentially many conic quadratic constraints, which are no longer linear anymore, right? So what's the strategy? How do we solve this problem? So now at least that we have built a motivation, how do we go about solving this particular problem? One thing is, one thing that you can try to do is not add any of these constraints to start with, right? So let
Can you give a pictorial example of this problem a little bit so that I'm also a novice, so maybe it'll help me understand a little bit.
pictorial representation. I mean, I don't. So, right. For example, here,
Yeah.
um, what do we have to do is we're sending. So, if x's were our decision variables, um, pardon me, if x's were my decision variables, which determined whether an arc is in the cut set. Um, no, let's see. How do I? So great. So let's say that what I'm deciding is whether I wish to have an arc um, built or no, right? So every time I build an arc, I need to pay some fixed cost. So clearly, building all the arcs that I need to pay some fixed cost. Now, do you get this particular constraint? Um, how we arrived at this constraint? So if you were to send some flow from here to here,
Mhm.
right?
Yeah.
Um, and let's say you have a partition,
Mhm.
right? So let's assume that this was our partition of nodes.
Mhm.
Then I need to make sure that at least the amount of flow is passing through this partition. So all the edges or all the arcs that are going from source set to sink set
Mhm.
must be able to carry that much flow. Does that make
Yes.
sense?
Yes. Yes.
Right? So that's what this constraint says. It says that summing over all the edges in the cut set, right? The capacity should be such that they're able to support the flow D.
Yeah.
That's all it's saying.
Okay.
However, here I assume that my capacities were deterministic, right?
Yeah.
But what if my capacities were actually not deterministic? They were stochastic.
Mhm.
Then the set of solutions is not deterministic anymore.
Yeah.
How do I optimize over it? Right? So
Yeah.
if I were to write this constraint,
Mhm.
where my parameters are coming from some underlying distribution or some uncertainty set,
Mhm.
you cannot give me a vector x that is guaranteed to satisfy this constraint for
Yeah.
all possible realizations of psi,
Yeah.
right?
Yes.
So the question that we ask is that the probability that this constraint is satisfied is greater than or equal to some service level,
Mhm. Okay.
right?
Okay. Yes.
And that's what I just said here. So that the constraint, if this constraint were to be satisfied,
Mhm.
um, there is a way that I can model it in a way that can be studied
Mhm.
through some algebraic and geometric techniques,
Mhm.
right? So this
Yes.
probabilistic constraint, I have just sort of again, rewritten
Yeah.
as a second order cone constraint. I mean, it's very easy to see that if the realizations were distributed normally, then or were sampled from a Gaussian distribution, then you can write this constraint or this sort of probabilistic constraint as the second order cone constraint. Not hard to see. But what is interesting to see is that even if that was not the case, right? Even if um, you had no idea about what the underlying distribution is, but you could compute the first two moments. Even in that case, you have a very good inner approximation of this probabilistic constraint, right? So
Yes.
every x now that you get as a feasible solution would satisfy this constraint.
So the moments
And
you're talking about is the statistical stuff which says
yeah,
that it will be
statistical,
average and
yeah,
then
so just the
standard
mean and the
deviation. Yeah,
variance.
yeah,
Yeah,
yeah, yeah,
the mean and the standard
yeah,
deviation again.
yeah,
So, or if, in another case, if your psi had a symmetric support, even then in that case, you will have a similar looking constraint. So the main idea here between these three slides is that no matter what your underlying distribution is, you can have an inner approximation of this probabilistic constraint through a constraint which looks like this, right?
yeah,
So
yeah.
that's the idea that I'm trying to develop.
Okay, okay.
And if that so happens, then even if we were able to sort of have that, um, we still need to add exponentially many of such constraints, right? Because there are exponentially many of such cuts, right? So here, not only just adding this cut for one constraint satisfies, you need to add this for all
Okay,
possible
okay,
cuts,
okay, okay. Now I see. Now I
right?
see. Now I
So
understand.
it
Yes,
doesn't
yes,
matter
yes.
where you, so if your
Sure,
pipe
sure.
was not able to support at every,
Yeah.
section of the pipe that you cut it at.
Mhm.
So, I mean, clearly the bottleneck is what you need to explore, right?
So the
Um,
worst case scenario that you are posing to 2 raised power n is the
yeah.
case where you have a linear chain.
Not necessarily a linear chain in any network that you can see,
Hmm.
right? Any network that you see, you'll need to add exponentially many. So, I mean, it's just so you'll need to, let's say, you need, because you need to do a partition.
Hmm.
A partition could be just the source set here
Hmm.
and all the nodes here.
Yeah,
Then you can all have one partitions, right?
yeah,
Where
yeah.
just, so basically it's just a counting argument, right?
Okay,
So n choose 1 plus n choose 2 plus n choose 3 plus n choose 4
okay, okay.
dot to n choose n minus 1
Yeah, I get it. I
or
get it.
whatever.
Yeah, yeah.
So, right, so it'll just be 2 to the n minus 1. Um, so now instead of worrying about solving this problem as is, which is already hard and now we're dealing with exponentially many constraints, is that we don't add any of these constraints that we sort of derived or we know would probably work. And what we do is that we try to solve the problem without these constraints, right? So let's say you try to solve your problem over this larger feasible set. And this is your, after you add all the exponentially many cuts, this is your actual feasible set. So now, if you start optimizing over this larger feasible set, what you can then try to do is once you get a solution. So let's say if your objective is pointed this way, this is going to be a optimal solution, um, and then you cut it through your second order conic constraint, right? So now your resulting feasible set would be this particular region, and these constraints will be then. So essentially, what you're doing is you're figuring out which constraints do I need on the fly. So there you need a separation problem to figure out which constraints do you really need on the fly. And the the constraints to identify are not sort of super difficult. And again, this separation problem is going to be tricky with respect to whether you want to study this problem with sort of correlated capacities where your sigma is indeed um, your variance covariance matrix, full variance covariance matrix, or you want to study it with independent capacities, in which case sigma is just a diagonal matrix, right? So I'll try to deal with both the cases if I have time, but we'll definitely look at the case of independent capacities, right? And as it turns out that this particular set, right, which we have spent so much time, at least half an hour now, trying to motivate us about, is actually a non-increasing submodular knapsack. And I'll get to definitions of what submodular knapsacks are, but there is something very interesting about this particular about this set, both geometrically and combinatorially. So yeah, we'll see if we can get to correlated capacities. But in the case of correlated capacities, it's a non-monotone submodular knapsack, so there is no monotonic argument that can be made. But in the case of uncorrelated capacities or independent capacities, it is indeed a monotone submodular knapsack, which will look at what are the interesting things about that, right? Um, so just one small thing before we move forward. I told you that here we are going to add these conic constraints that we just figured on the fly, right? We'll add them as we need. So let's say you optimize your problem over a smaller set as you figure that it does not. Let's say your problem gives you a solution such that it does not satisfy um, this probabilistic argument for this cut. So you just add this cut instead of adding every cut. And then again, in the next iteration, the solution you get does not satisfy the probabilistic argument for this particular cut. So then you add this cut. So right at every juncture, every time you find a solution, you try to find out what the bottleneck is, and you just add the constraint for that bottleneck cut set. But how do we even find what is where the bottleneck is? And that we can easily achieve through something called a minimum cut problem, right? So a minimum cut problem, I mean, I'll not go into details of this because I want to highlight sort of what is amazing about this particular constraint set. But just know that there is a separation problem, and that can easily identify which cut sets to add. So if you do want to know about this separation problem as well, we'll see if we have more time, then I can come back to it. But right now, I want to focus on this this idea of what submodular knapsacks are and how can we deal with them, right? So that the idea here is not basically just address this minimum cut problem. And if you're already aware, so at least for people who are aware of what a minimum cut problem is, I'll just quickly sort of go over this. So this is your typical minimum cut problem, right? You want to partition the network such that you can find out what is the bottleneck or what is the cut set with the minimum cut capacity. And now we want to find out a cut set that satisfies um, the minimum cut with this cut capacity, right? Because this is our robust cut. We want to make sure that this is greater than or equal to D. So if the solution of this does tell us that there is a cut, there is a realization of some cut which is less than D, or if the optimal value of this solution is less than D, then we can correspondingly just add that cut into our master problem. And these essentially set of constraints just make sure that you're only counting the arcs that are going from source to sink. Not there might be some arcs that are coming back from sink to source. You're not counting those. You're only counting the arcs that are going from source to sink. So that's simple. Now the problem here with this particular formulation is that this in general is an NP-hard problem, and because you need to find your these bottlenecks again and again, you solve your master problem and you come back to the separation problem, find something that is not satisfying some of the constraints here, you add that constraint, you solve it again, you come back to it, right? So this back and forth between master problem, so you solve master problem and then you go back to separation problem, and separation problem tells you whether you have the optimal solution if this value is greater than or equal to d, or it tells you that this value is less than d and you need to add a specific constraint to the master problem. So the cycle keeps going on until this gives you a certificate that yes, you've satisfied solving this problem and you have an optimal solution. So if this problem itself becomes hard to solve, then there is no hope of solving this particular this particular big problem. So we need to figure out at least how to solve this problem fast, because we need to solve it tons and tons of time. So one easy way is to just reformulate this particular problem and use the trick that in the case of independent capacities, you can write this term, which is nothing but sum of sigma ij, zi, zj, I and j ranging from 1 through whatever. Um, in the case of independent capacities, you will have it as summation I is equal to 1 through n sigma I squared xi squared, right? Because sigma ij is 0 and you only have diagonal matrix, this thing is still non-convex because this is going to be somewhat of this form, right? So anyone who has sort of some idea of convexity knows that this constraint is non-convex. So how do we sort of how do we take care of that? We can just use a simple argument, right? That in the cases of binaries, because our z's are binaries here, in the cases of binaries, or I mean, I'm sorry, this has to be z. In the case of binaries, z squared or z squared is essentially z, right? So now, wherein this this is a convex function, it's not hard to see, is a concave function. Its square root is a concave function. Norm is a convex function. So now you have a problem that is convex, and it can be solved pretty fast. So that kind of takes care of that. That's a simple trick. Nothing super interesting there. But at least we can solve this separation problem, which we need to solve many times, fairly fast. So that takes care of that. Now once we figured out what to do with our separation problem, let's come back to the main problem that we have to focus on. So if you keep adding these constraints to our main problem, let's say we have solved it for some cards and we've added a few cards. Now, how do I even solve this particular problem? That's what we are going to look at. So I'll just develop some preliminaries first of all. Let's consider a index set n. So let n be an index set. Let n be, just your index set ranging from 1 through n, a finite index set, and let f be a set function on, right? What I mean by that is that let f can be just a 0 1 set, right? So let's say alpha xi, where xi's are 0 1. So xi is, or x rather in this case, is just a characteristic vector of what index or what choices of indices you choose. So, and with respect to this set function and this finite index set, let's consider a difference function with respect to the set, right? So, what this rho is denotes um, is what we call as the contribution of element I to set S, right? So, here, with respect to this example, right? With respect to this example, um, let me take any set S, which is a subset of N. Let S be 1, 4, 5, 7. So f of S then is um, alpha 1 plus alpha 4 plus alpha 5 plus alpha 7, right? This is f of S. And rho is essentially f of S union I minus f of S, right? So in this case, we know that rho is. So what is rho is in this particular case? In this case, can someone tell me? So you've given this function here. What is this difference function with respect to any I and any S? Akshay, do you have an idea? Are you following?
No, I was just looking at something else. I was trying to
Okay,
make one.
okay. Anyone here? So what is F S union I here? So let's say I was 3, right? So S union I will be just 1, 3, 4, 5, 7. And f of S union I will be alpha 1 plus alpha 3 plus alpha 4 plus alpha 5 plus alpha 7 minus f of S. So what is remaining there? Just alpha 3, right? So rho I of S in this case will be alpha I. And now we'll present a characterization of submodular functions that was given by Laszlo Lovash in 1983, which says that f is submodular if and only if. So this is a necessary and sufficient condition. And it says that f is submodular if and only if this difference function is decreasing in the size of your input set, right? So if t is bigger than s, or s is a subset of t, then rho I of s will always be greater than rho I of t. So it depends whether you are adding the element I to a smaller set or a bigger set. The contribution decreases as you go further, or as the contribution of a specific element decreases as the size of input set increases, right? So that's fairly simple. And any such function that satisfies this condition is called a submodular set. So one example would be, let's say this, right? Um, so clearly this function is not submodular because here rho I of s, irrespective of which, this rho I of s is independent of s, right? So it doesn't matter which input set I add I to, my contribution is also always going to be alpha I. So these sets are called modular sets. And we're looking at submodular sets. That is, the bigger the input set, the smaller my contribution, right? So for example, if my set was something like this, x1 plus x2 plus x3, um, plus square root of x1 plus 2x3, right? So if you see contribution of 1 when your s is just 2 is bigger than when your s is 2 comma 3, right? So rho I of s in first case is what? So let's say x2 was already 1. So now if I add, I'll keep x3 as 0 and I make x1 equals 1. So my function value becomes 2 plus 1, 3. So my rho I of s is essentially 3 minus 1, which is 2. And if 2, 3 were already 1 and then I add x1, then my function value becomes 3 plus square root of 3. So rho I of s in that case is essentially 3 plus square root of 3 minus 2 minus square root of 2. And you can verify that this is going to be smaller than this number. So, some modular functions kind of occur in our day-to-day lives. Any kind of utilities, right? We say that, oh yeah, consider this function that occurs naturally, right? So you go out eating ice cream, or you go out trying to eat chaat. So after you've had a few pani puris, the urge to have the next pani puri is going to go, smaller and smaller as you've had more pani puris. So basically, modeling utilities is a submodular function. So these submodular functions kind of occur fairly naturally. So now here is a good characterization of a submodular function, right? At least in the form that we need. So if a function is defined as this, right? So it's basically talking about two components. First is, so when I say A of S, it just means summation over I, AI, Xi, for I and S, right? And so it's talking about two components in G of C of S, where C of S is similarly defined. So if G is concave and C is the vector C, so this is essentially going to be G of summation over I and S, CIXI, or just CI for that matter, not even XI. Yeah. So if C are all positive, C is a positive vector and G is a concave function, then any function of this form is going to be a submodular function. And now, if you look with respect to what we had, right, we had something of this form. We had U transpose X minus sigma square root of summation sigma I squared xi, right? Greater than or equal to d. So let's get it into this form, f of x less than or equal to b. So I multiply everything by -1, which makes it u transpose x plus omega summation, right? So I'll just edit the first thing. I'll just multiply it by -1. And this then becomes, yeah. So now focus on this function, right? This function. This is a function of this form, right? This is our a of s. Since x is 0, 1, this is a set function. G is our square root function, a concave function, and this is c of s, and we have all the c's positive because it's sigma I squared, right? So now we know that this function is a submodular function, and this set is a submodular knapsack set. So at least we found something combinatorially interesting about our set that we were considering, right? That it's a submodular knapsack set. Now, how does this information about the combinatorial nature of this underlying or this underlying nature of this polyhedral set can help us? So first of all, I guess I said that, but I'm not sure if most of the folks here would follow. Um, can you so let's look at all. So I just said that this set this set convex hull of this is a polyhedral set. Do you guys agree? I mean, it's clearly there is some nonlinearity happening here. Um, and we know that, well, polyhedral sets are defined by the intersection of finitely many hyperplanes, or half spaces, sorry. So, right, irrespective of what you have here, right, all the solutions are going to be 0, 1. And if you look at the convex hull of all these points, which are just, so you're looking at some subset of the vertices of an n-dimensional hypercube, right? And that is always going to be a polyhedral set, irrespective of what. But what we are interested in is looking at the facets of that set. Because if we can find out the facets of that set, then we're in game. We can solve this problem really fast. So for the case where f was non-decreasing, right, we have to, if you see here, while this particular function is submodular, um, there is another specific monotonicity property of this function that will help us. And before I go there, I want to identify that the case when f was not decreasing was already covered by Adam, Turk, and Narayanan. They defined some submodular cover inequalities, and um, what this set says is that now forget what we are looking at, right? We have identified that the set we are looking at it a submodular knapsack. Now let's look at this particular case of non-decreasing submodular knapsack. So imagine now that you have a submodular function on a finite index set, right? So let f be submodular on some n, and consider a submodular knapsack set, which is again we all know how to define that: f of x less than or equal to b, x belonging to 0, 1, n. And now imagine that f is non-decreasing, and f is full dimensional, or x is full dimensional. These assumptions are just making sure that things are nice, and nothing is super crazy. So, except for the first assumption, which is sort of more defining in nature, these two can be made without loss of generality. Um, and if that is indeed your set, I would like to introduce the notion of what are covers or some sort of forbidden minors or infeasible solutions, right? So if this was the set you were interested in, if this was particularly the set you were interested in, um, any solution such that f of x was greater than b would be an infeasible solution, right? It will not be a feasible solution, or it will not any x in 0, 1 such that f of x was greater than b will not be in x, capital X. So now that gives you some idea that if you do find out a solution through some way, which is an infeasible solution, what can you say about that? So we call that solution, that infeasible solution, a cover for X, right? So a subset S of n is a cover for X if f of s minus b is greater than 0. It's strictly positive. So f of s is greater than b. So that's an infeasible solution. Now, if you look at a restriction of x, right? So project it onto this space. So if you look at this restriction of x, such that for all the indexes which are not part of the cover, you set xi is equal to 0, right? And you consider this restriction of the set x. Now, there's a pretty interesting result, right? So what this says is that consider for everything that is not part of the cover. So let's say we had 5 things here, right? Let's say this had size 1, 2, 3, 4, 5. And my bag has size, let's say 7. Uh, my bag has size 7. And more, I want to include um, these things in the bag. So a feasible solution is I can put 1, 2, and 3, right? Because the total size then becomes 6. And I can put them in my bag. Can I put 3 and 4? Yes, I can put that as well. But can I put 4 and 5? No, I cannot. Right? Um, so that becomes a cover. 4, 5 becomes a cover, right? Because f of 4 comma 5 is equal to 9, which is greater than 7. And does that give me, and if I, say that, don't consider, imagine that these 3 elements were not there. Then what can you say about any feasible solution over this restriction? you have to say that at most one of them can be one, right? They both can't be one simultaneously. Because if they're both one simultaneously, or if they're both included, then that will never lead to a feasible solution. So we define these inequalities. Okay, first of all, I'll need to, just by a raise of hands, if you can you tell me if you're familiar with the branch and bound algorithm, or how to solve discrete optimization problems? That is going to be a little important here. Is anyone here familiar with solving discrete optimization problems through branch and bound?
Anyone? I can't see any raised hands.
Yeah, I don't either. So I believe because this might be a little tricky if you if that is not so okay. Do people understand or are you guys aware with or aware of how to solve linear programming problems? Are folks here familiar with linear programming problems and simplex algorithm at least?
So traveling salesman is a typical, I mean, that is the showcase linear programming problem, right? Traveling salesman.
Yeah, that's a that again that's a it has a combinatorial nature and has cutting planes as well. So if people are aware of traveling salesman, then this should be fairly straightforward for me.
So Saroj Kant says that yes, he's aware of it. I think most of us are aware of the traveling salesman problem.
Okay, so if you're aware of traveling salesman problem, right? Um, you remember how so if you solve traveling salesman problem, one of the key things if you don't include any subtour elimination constraints, right?
So is it possible for us to briefly describe the traveling salesman problem,
Yeah.
because it is posed in
So
different ways?
yeah, yeah. So let's say that you know, so I'll take one of the empty slides that I kind of had before. Yeah. Let's say that you were given a set of nodes or some cities that you wish to traverse, and there is, there are edges that are connecting. So imagine them being the roads that are connecting these cities, and you have to travel. I mean, of course, every city, every edge has some cost. You could consider it time from going from city I to city J, right? So every city going from city I to city J, let's say we pay a cost Fij. So how do we? What's the optimal way of traversing all the all the cities and returning back to your original place? Or how can you you know travel all the cities for minimum cost possible? I guess that's how I would describe it. I mean, in general, how do how have you looked at it, Akshay?
Yeah, I mean, the last series. So my knowledge comes from the workshop that I have monitored.
Oh,
So
okay.
simplex method, for example, we did last time. So
Uh-huh.
Mr. Nikhil Tatke is saying that he's aware of simplex method.
Okay, sure. So, what happens in simplex or linear programming problems. So even in discrete optimization, right? So what happens is now you're looking at so in discrete optimization, let's say this is your polyhedron, right? These are extreme points of the polyhedron. When it comes to discrete optimization, you're looking at lattice points inside this polyhedron, right? Because again, for obvious reasons. Um, and you're not looking at the bigger polyhedron itself. So if you do use simplex to solve a discrete optimization problem, your solution is going to be somewhere on an extreme point, which need not be an integer point. If it is an integer point, great, you're done. But if it is not an integer point, what do you do? So let's say that I was solving this problem: minimize x plus y uh, plus 3.1z, and subject to some x being sorry, these xyz following some constraints. Let's say I would rather say x1, x2, and x3 here, and ax, let's say, equals to b, x greater than or equal to 0, and x and z, right? So let's say when you run simplex, one iteration of simplex, you get x1 is equal to 1, x2 is equal to 2.2, and x3 is equal to 2. So how would you progress from there? So what branch and bound does is that it branches on x2 and it divides the problem in two particular sub-problems. In one problem, you will have x2 greater than or equal to 3, and in the second problem, you have x2 less than or equal to 2. So along with these constraints, you'll add another constraint. In one problem, you'll add that constraint, and in the other problem, because it cannot be between 2 and 3. And each of these problems, so when you did not have these constraints, they'll give you some lower bound on the optimal value, right? Because you're optimizing over a bigger set. And when you include these constraints, you're continuously going to get upper bounds because you're optimizing over a restricted set. So what you do is you keep bettering your lower bounds and upper bounds, and arrive at a solution, and that's going to be, so when your upper bound, which is obtained through feasible solutions, meets the lower bound that is coming through relaxation solutions, joins together, that's going to be your optimal solution. Now in general, what happens is that if you're first, so by default, the first step in solving a discrete optimization problem is solving the continuous problem. So it doesn't matter how many discrete variables you have, how many variables take on integer values, you relax them to linear programming first. You relax them, all of those to being continuous variables, and you solve that problem. So obviously, you are looking at a much, much bigger problem. So if this was the set of all discrete points, right? I mean, obviously, I have drawn it wrong, but whatever. Um, and this was this, this was if you were to relax all integer requirements, the farther, since you need to cut off this much, set of solutions, these solutions are not feasible for your integer programming problem. So yeah, so another way of, because see, you're working in a branch and bound, you're working with improving your lower bounds and upper bounds. So one way to improve lower bounds, if you can chop off, this the solution space. So if you were to only restrict this part, your lower bounds are going to be better because you're working with a smaller relaxation. If you can chop off this as well, you're going to be working with much smaller set in that case. So again, better bound. So if you could get, the idea is to get these, right? If you can get these, you can just use simplex, one iteration of simplex, and um, that'll give you the solution. But until you have that, you need to keep coming up with ways to chop off, you know, this extra space, and that's what we're trying to do here. These are called cutting planes. Um, these constraints that chop off the solution space, and here that's what we are doing, right? We said that in this case, if my solution consists of both 4 and 5, then there is absolutely no way that my solution is going to be feasible. If 4 and 5 were both 1, that will not lead to any solution that can be in X, right? So we have this constraint here, which chops off the region such that um, the continuous solution space, and we obtain one such constraint. And similarly, you can derive other constraints. Similarly, if you have um, 5 and 3, you can write the similar constraint for 5 and 3. So 5 and 3 both cannot be 1 in any solution. So x3 plus x5 is less than or equal to 1. So that's what this says. Xs. So if S is a cover for X, then the cover inequality is X of S, or basically what it says is that summation of Xi INS is less than or equal to cardinality of S minus 1. Why? Because if all of these X's were 1, then this right hand side, sorry, this left hand side will be equals to cardinality of S, right? But they cannot all be 1 simultaneously, so they have to be less than or equal to cardinality minus 1. So it just says that if S is a cover for X, then this cover inequality is valid. That means it preserves everything that needs to be preserved, and it cuts off something which should not be preserved, and it defines a facet. So it defines one of the face defining inequalities if and only if S is a minimal cover. What is the notion of a minimal cover? A minimal cover means that if you take, so here, for a cover, we said that it's an infeasible solution. Minimal cover is that if you take anything out of a cover, it becomes a feasible solution, right? So here 4, 5 was a minimal cover. Why? Because if you take anything out, if I take for 4 out, it becomes a cover. If I take 5 out, it becomes a cover, right? So this inequality is a facet defining inequality. That is, if I was working with a problem, that I was kind of looking here, it'll be an inequality that defines these facets, instead of just a generic inequality which cuts off some region, right? So those are the arguments of these sum modular covers, and then you can further strengthen them. I mean, I'm not going to go into algebra here, but I'll tell you that how it fits into our problem of network design with uncorrelated capacities, right? So we said that this was what we got to, right? Uh, we had a submodular knapsack. However, um, it is not necessarily monotone, right? It's not necessarily non-increasing, non-decreasing. I mean, we don't know. However, it can be non-increasing if this is satisfied, if AI, or if in our case it was minus UI, and whatever you knew what we were doing. Um, let's say it was UI minus omega square root of summation sigma I squared xi, right? So if ui is greater than or equal to omega sigma I, then this function is non-decreasing, and the negation of it is non-increasing. Um, And if you rearrange things, this essentially becomes a simple requirement on the coefficient of variation, right? And that's not a super big, super high assumption. So if you assume that your coefficient of variation is bounded above by some constant, um, what we have here, then you get monotonicity as well. And how does that help us? So here our function is non-increasing. So we just looked at non-decreasing submodular knapsacks, right? So here in our case, we are looking at non-increasing submodular knapsacks. Um, so let's make similar kind of assumptions that we call it either it can be considered non-increasing submodular knapsack or non-decreasing supermodular knapsack. So basically, it's just a matter of negation. But don't let this notation confuse you a little bit. But consider we were, what I mean. You can also look at if this was presented in this way, then f was non-increasing submodular function. And we're looking at the lower level set of this function. In this way, it's a supermodular covering knapsack. So covering sets are of this form, and just a negation of this thing. Nothing super crazy. So basically, what we're saying is that we have covered non-decreasing. The second step is to figure out f non-increasing. So what happens when f is non-increasing? So similarly, as we had earlier, we'll define a notion of an infeasible solution, right? So what is a feasible solution? Any solution such that f of x is greater than or equal to d, right? That is a feasible solution. So what will be an infeasible solution? F of x less than d, right? Um, and if this was indeed the case, what will be your valid inequalities now? What will be the valid inequalities now? The valid inequalities will be that if I add anything from the complement set and if it makes it feasible, right, then at least one of those elements needs to be added to this infeasible set. So, right, in this case, I call it a pack, right? In the previous case, we called these infeasible solutions a cover, but uh, a pack um, is defined as an infeasible solution in this particular case for covering knapsacks. So consider a subset of n, a pack, if f of p is less than d, right? So as we have described here. So if indeed this is satisfied, um, then we have an infeasible solution. And if you consider a restriction such that you project the set on xi is equal to 1 for all i's that are in the pack, then we say that at least one element that is not in the pack should be included, right? So it's very sort of intuitive that, hey, with whatever I have, I'm not able to support what I need to support. So at least something from what I did not add, or essentially P was my pack and the complement set is N minus P. So at least something from N minus P should be added to the pack to make it feasible, right? So that's why this is valid for X and it defines a facet of convex Hull of this restriction if and only if P is a maximal pack. Again, the notion of maximal pack is similar, that if you add anything from the complement of the pack, it becomes a feasible solution, right? So if you add anything from the complement set to uh, the pack, it makes it feasible. So for a pack, it is less than D. You add anything to it, it becomes a feasible solution. It satisfies f of x is greater than or equal to D. So that's the notion of. So again, anywhere here we did not use the submodularity aspect of uh, of a function. We just used the monotonicity argument. We just used the fact that they were non-decreasing or non-increasing, right? Um, However, um, if you were to, so by themselves, these inequalities are not strong at all. Um, because you're just using the monotonicity argument. So by itself, these inequalities do not cut off a lot of section that needs to be cut off. So we need to extend them, right? So one way to look at this is that if you were, let's see, um, let's look at this argument, right? This is x less than or equal to 1, all this, when xy greater than or equal to 0. So this inequality is weaker than this inequality, right? Because um,
Because it chops off more area.
much smaller set,
Yeah.
much smaller set. So clearly, this inequality dominates this inequality. And that's what I mean when I say that because we do not have all elements of index set n in this inequality. We have only the elements from the complement set. So how can we bring elements from um, the pack itself to this inequality? So can we somehow um, bring the elements of the pack, or with some, I guess it'll be with some coefficients, and also something here, that this inequality. So adding anything here is going to uh, you know this has to be less than or equal to cardinality of p. But we just want to lift the inequality in higher dimensions to make it stronger, and that is when we kind of use the submodularity argument of these knapsacks. So for example, if this was the conic quadratic min knapsack set, right? If this was what you were considering, um, you have minimal packs as 1, 2, 1, 3. So if you take 1 and 2, that's a feasible set, right? Sorry, that's not a feasible set. 1 plus 2.5 is 3.5. It's less than 5.5. So it's an infeasible set. So this is a pack. And clearly, if you add either 3 or 4, it becomes a feasible solution. So it's, of course, a minimum maximal pack as well. Similarly, 1, 3 is a maximal pack, 1, 4 is a maximal pack, and 3, 4 is a maximal pack. And the back inequalities correspondingly is. So here, if you see that in any feasible solution, at least one of the x3 or x4 has to be greater than, has to be equal to 1, right? They can both be 1, but at least one of them has to be 1. And similarly, so on and so forth. So all feasible solutions of this set satisfy all of these inequalities, which you can verify. And so these extensions that I'm talking about, right, where basically the argument is very, I mean, the argument is that if I remove something from the pack and its contribution in a particular permit, I mean, it's a tricky argument that utilizes some modularity of air, which I'm not sure is consistent with what we know. So I won't go into much details. But the argument is that if you use the submodularity of this function, right, you can extend these inequalities. So this inequality, which was x1 plus x2 greater than or equal to 1, now becomes x1 plus x2 plus x3 greater than or equal to 2, and so on and so forth. So these become much stronger inequalities, and that's the idea. So pretty much all of these things can be utilized. I guess we are running a little short on time, so I'm not going to discuss most of the stuff. But I'll just show you some of the computations, right? So just to give you some idea of what is the effectiveness of adding these inequalities and using these combinatorial structure. So Cplex, if you don't know, is one of the state-of-the-art solvers, right? That solves these problems. Now, what we and it can solve problems using two ways, right? It can solve, because these are nonlinear programming problems, it uses the geometry. It can either use barrier function or it can use an outer approximation function, which is by linearizing the whole set. It solves these problems. And it turns out that when we solve these problems, right, on um, where our number of variables are ranging from 25 through 75, and our constraints are ranging from 10 to 20, you see that on an average, this is the root relaxation gap. That is the gap between your first lower bound of the root gap. I mean, so the first time you solve this continuous relaxation through simplex method, the the percentage gap between that solution and your optimal solution, right? How far was that? So if you see, Cplex by default, running all its cutting planes, has an average root relaxation gap of 14.5%. On an average, it explores these many nodes. And primarily, it cannot solve majority of bigger instances. So we try to solve 5 instances, and Cplex could only solve, in some cases, well, using outer approximation, it was able to solve majority of the instances. But if you use the extensions, the extended pack inequalities, or I mean, the inequalities that we develop, right? If when we try to explore the combinatorial structure and not just the geometrical structure, look what happens here. So, I mean, these root relaxation gaps, that is, we have squeezed by cutting these extra sections off, right? We have come almost within 3.4% of our optimal solution without even sort of going into the branch and bound tree. And the number of nodes that we need to explore in the branch and bound tree reduced by a great factor. So the motivation here is to, when you're looking for these 0-1 kind of problems, to not only study the geometrical structure, but study these underlying really intriguing combinatorial structures as well. And these combinatorial structures can give you more um, sort of, bang for your buck than understanding the geometry, especially when it comes to 0-1 programming problems. So that's kind of the gist of what I wanted to say today. We had fairly a lot more interesting graphs, but I don't have time to sort of go through most of it. Um, this is a fairly advanced topic, I understand. However, if any of you are interested in this and want to get in touch with me, I think um, you can contact me. I think the organizers have my contact details, and I'd be more than happy to talk to you about these things. Um, I definitely really like these combinatorial structures, and if there's anyone who wishes to talk to me about these, I'll be more than happy. Yeah.
Uh, I think you are the right person to give us a lecture on various mathematical language structures. I mean, let me put it that way.
Okay.
So I have a very tough time reading
Uh-huh.
through maths because the first part of that goes in debug, not debugging, but in declassifying the mathematical language that is there. So I have really hard
Yeah.
time doing that, and then I come to
Oh,
the actual topic. So
okay. I mean, this is definitely, I mean, so that unfortunately is what kind of deters us from, you know, like the struggle is if you get passed through
yes,
that, right?
yes, yes,
That's when you see the beauty of the
yes,
map that lies. I
yes,
mean,
yes,
but most of us don't even get past
yeah,
that.
yeah,
Like we just
and
stop right before
yeah,
that.
and unfortunately, that language is necessary because without that language,
Yeah.
you cannot do much.
Yeah, that's true. That's very true. And some of these things are actually, the more you look into them, the
Yeah.
more amazingly, yeah, they're super amazing. And
So
yeah, I mean,
next time we have a lecture from you, I'll
yeah,
insist that we do it in two parts. The first part
sure.
is about mathematical language,
Just,
and the
yeah,
second
just
part is about the
developing the
actual
base.
content. Yeah.
Sure. Yeah, I guess the next time I can probably, unfortunately, yeah, I did not realize, I was not aware of, um, I guess after looking at several other topics, I figured that I should have probably just discussed, if I would have just discussed discrete optimizations,
Yes. Yes.
I
Yes.
guess that would have been a better topic. I
I
wasn't,
I could relate to it a little bit. I mean,
yeah,
when you were talking about that convex, I don't know mathematical language,
yeah,
but
no, that's,
but
yeah,
I think I could relate it to it a little bit in the terms of that you are using so it's like a triangle, right? So if you have three sides,
yeah,
the sum
yeah,
of the three sides in length will be smaller than the actual
yeah,
extent of the triangle.
yeah. In
So
some ways, yeah,
something like that. So
yeah,
I guess that way we are trying to reduce some
yeah,
constraints to reduce the space and stuff like
yeah,
that.
yeah, yeah, yeah,
So, so
indeed.
uh, any of the participants have any questions? No? We might have some mathematicians in the crowd though.
Yeah, I mean, I'm sure there must be some.
Uh, am I audible, sir?
Yes, yes, you are.
Yeah.
Okay. Hello, sir. This is Gyanaranjan Patra from Shiksha Anusandhan Bindu University, Bhubaneswar, Odisha. Sir, can you cite some practical examples where this submodular snapshot problem is used?
Oh yeah, so submodular knapsacks, for example, you know, anytime when so I guess when you're dealing with decision problems, when you have 0, 1 variables, right? Um, and you're working with a risk measure, which involves sort of, if your risk measure is value at risk, right? So if you're working with the worst case scenario kind of optimizations. So for example, if someone wants to optimize their portfolio, um, so in the similar setting, right? If you wanted to say that, oh, the probability that my portfolio gives me this much return, and the nominal return is known and the standard deviation is known, then you can sort of characterize it as, again, a submodular knapsack set. In this case, where we had a network design problem and we wanted to address those cut set kind of inequalities, then that also gets formulated as a submodular knapsack problem. Any quadratic constraint in 0, 1 variables, right, can actually be represented as a submodular knapsack constraint. However, it may not be monotone. So, so this basically provides a great general framework to explore. I mean, when you have quadratic constraints, um, there's not much. I mean, you can utilize the geometry, but that doesn't yield you anything. Because at the end of the day, if all your solutions are 0, 1, you're working with the vertices of the hypercube, right? Um, that's essentially and basically some section of it. So not much can be obtained just by utilizing the geometry. So if you understand these combinatorial structures, they provide you great ways of you know solution procedure. So modeling wise, I would say, I mean, yeah, there are things that you can, you know, anything that you model when you have uncertainty and if you're using value at risk, you can actually you end up um, with these kind of submodeling knapsacks.
Thank you, sir.
Yeah.
Okay, so thank you, Professor Mahajan, for giving us this wonderful talk, some aspects of mathematics as well. See, I am not a mathematician, so
No, no, no. I mean, I guess most of us weren't really. I don't classify myself as a mathematician either. My wife is a mathematician.
no,
She's a pure math
so that is
person.
why you are the right bridge. So you can help us
I guess.
understand that.
Sure. I mean, and I definitely apologize. I guess this talk was probably not addressed to the audience primarily. I mean, I think the next time I will make sure that
See,
it's actually a
the
lecture.
purpose of this talk is not to enlighten them. The purpose of
Yeah,
these talks are just to give them pointers so that those who are interested can follow the
yeah,
lead.
yeah.
So,
I
so
guess that's yeah. Then I'm glad that
yeah,
this
yeah, yeah.
because yeah, I mean, most of the other talks are sort of exposition to what is up there.
The MDO
Yeah.
is also a similar kind of topic. So a handful
Uh-huh.
of us are working on it. But for example, me, before I did started this workshop thing, I was completely unaware of what this MDO is. And once I started looking at the lectures, then
Oh,
I realized it's only that the language is English there, but in
yeah,
mathematics, the language is maths.
yeah. No, that's true. That's true. But it's, I guess, it's almost like, yeah. I mean, if you're well versed in, I mean, I think of mathematics as a language, right?
Yeah, yeah,
If instead of just as these um, weird structures that we can't understand. The moment you start looking at it as
yeah,
language,
yeah,
and the moment you're willing to understand the grammar and the
yeah,
you know
yeah.
those things,
So
then it's actually very interesting to understand some like then you start seeing these things as
yeah, yeah,
poetry,
yeah, yeah. No,
and
no. I mean,
yeah,
I complete. So I had to look into this something called these Bessel's functions.
yeah, Bessel
For
functions are pretty interesting.
So I
Yeah,
had to read mathematics for that and
yeah,
trying,
yeah,
and after I understood what they were talking about, some lingo there, then
yeah.
it's beautiful. It's good.
It is beautiful.
Set
Yes,
theory is,
I
I think,
mean,
one area where I
yeah.
need to brush. I need to read more.
So I mean, I mean, in case people are interested in journal, just so I have an avid interest in number theory as well. So I mean, I have a lot of books just on number theory. I don't do number theory. I think I'm not smart enough to do number theory, but I just like reading about number theory. So if people are genuinely interested in mathematic puzzles, there's a beautiful YouTube channel called Three Blue One Brown,
Three, what?
and it's called Three Blue One Brown.
Okay, three
Uh,
blue, one brown. Okay,
yeah, you should try to look at it. I think
sure,
the
sure.
guy has an amazing way. Like so I guess it kind of motivated me to like he has first of all he has amazing mathematical knowledge and on top of that he has an amazing way of explaining that as well.
Okay, okay,
So I guess anyone who is trying to get into teaching these concepts as well can take some pointers from there. It's actually pretty interesting. Yeah.
okay. Thanks, thanks. So I'm just writing
Yeah,
it down in the
sure.
chat so that I don't
Yeah,
forget. Mr.
yeah.
Tatke has written
Yeah.
the. Okay,
It's three
thanks.
blue, one brown.
Three
Yeah.
blue, one brown.
One
Yeah.
brown.
One brow. Okay. Three blue, one
Brown,
brow.
brown.
Okay. Okay.
Yeah.
Okay.
So it's basically his this person's eye,
Okay.
like it has one shade of brown and three shades of
Okay.
blue. So
Okay.
that's it's
Okay. Okay.
it's pretty
Okay.
interesting.
So I definitely
Wonderful.
see that you have had a very good marriage. Good marriage.
Uh-huh.
You
I
have.
mean, I like so yeah. Both me and my wife we discuss math quite a lot. Like
Yeah.
just general discussions are pretty interesting. Yeah. Yeah. She's a mathematician here at TIFR.
Okay.
So.
Okay. Okay. Nice. Nice.
Great. Thank you.
One of the rare combinations.
Well, I just am glad with the combination. I don't care about the rarity, but yeah, uh, wonderful. I mean, thank you all for your time. I mean, I guess that's for just willing to listen to this this stuff.
Thank you for sharing your knowledge with us and give us some
I'm
pointers on a new direction.
I'm glad that I was able to at least enlighten some of you, hopefully, about this stuff.
So we are already, I think, 10 minutes ahead of
Yeah,
where we should be,
yeah.
and we have Professor Amuthan already with us.
Okay.
Good evening, Professor Amuthan.
Hi, good
Hi.
evening. Nice to see you all.
So I see you have increased your weight a little bit. I mean, apparently. No?
Yeah, my weight keeps fluctuating and by and large at a very high average. So,
Yeah.
yeah. Yeah.
So you can start
Okay.
whenever you are ready.
Yeah, sure. I mean,